A concave lens forms the image of an object such that the distance between the object and the image is 10 centimeter and the magnification produced is 1 by 4. The focal length of the lens will be. So we have to tell the focal length of a concave lens. And what is happening? Our concave lens is producing an image. The magnification is given to be 1 by 4. And you can see our virtual image is actually smaller in size than the size of the object. Okay? Okay. So this is the magnification. Magnification is given to be 1 by 4. And we have to tell the focal length. So we have to find out what is the focal length of this lens. Now, do we remember the formula of magnification? In cases of lens, what is the formula of magnification? Magnification is equal to V by U. Correct. Now, if you tell me this formula, let's assume something. Let's say that image is at a distance x from this lens. So, V is nothing but minus x. We take minus because the direction of incident light rays is taken as positive and the opposite direction is taken as negative. Therefore, our image is formed on the negative side. That's why we are writing V is equals to minus x. And let's say our object is at some distance from the lens. Can we find this distance in terms of x? Yes. So let me use the formula. Magnification is equals to V by U. Magnification is given to be 1 by 4. And what is V? V, I wrote it to be minus x. So what is U? U is nothing but minus 4x. Okay. So our object is at a distance of 4x from this lens. Our object is also on negative side. Correct. Now, the distance between object and image, this distance was given in the question. This distance was 10 centimeter given in the question. And we can see this is nothing but 4x minus x. This is 3x. So 3x is 10. 3x is equals to 10 centimeter. X is equals to 10 by 3. Okay. Now, we know what is the value of V. V is equals to minus x. This becomes minus 10 by 3. And what is U? U is minus 4x. This becomes minus 40 by 3. Now we know what is V, we know what is U. Can we find what is F? Yes. We will apply the lens formula. Tell me, what is our lens formula? You will say lens formula, that's so easy. Lens formula is 1 by V minus 1 by U is equals to 1 by F. Correct? Let's apply this formula. So let me place some values. So 1 by V. So this becomes minus 3 by 10 minus 1 by U. What is 1 by U? 1 by U is minus 3 by 40. So minus minus becomes plus 3 by 40. Okay. This is equal to 1 by F. Now from this you can see what are we getting? We are getting F to be about 40 divided by we have 4 3s are 12 and minus 12 plus 3, this becomes minus 9. Okay. So we are getting minus 40 by 9. Now this means this is nothing but minus 4.44, something like that. So this is our focal length. So our focus is obviously on negative side and our focus is at a distance of 4.4 centimeter from this lens. So this is our focus. Okay? Okay. 4.4. Now let's see the options and we can see that option D, 4.4 centimeter is the right answer for this question. A luminous object is placed at a distance of 30 centimeter from a convex lens of focal length 20 centimeter. Now let's imagine a convex lens. So this is a convex lens. So beautiful. Now at a distance of 30 centimeter from this lens, we have a luminous bright object. So this is our object shining brightly. Now the distance between the object and the mirror is given to be 30 centimeter. Cool. The question says the focal length is 20 centimeter. So you can imagine the focus would be somewhere over here, 20 centimeter from the lens. So we know f is equals to 20 centimeter. Now the object is beyond focus. So this means that we will get a real image of this object. You can imagine the light rays emerging from this object, and after refraction, they will go and meet the principal axis somewhere over here. We will get a real image. Okay? Yes. So we can see these light rays. Awesome. Now, the question says that uh, on the other side of the lens, at what distance from the lens a convex mirror of radius of curvature 10 centimeter be placed in order to have an upright image of the object coincident with it? I will explain. See, we have to use a convex mirror. This is how convex mirrors look like. Now the radius of curvature of this convex mirror is given. It is 10 centimeter. Okay? Yes. Now, we have to place this convex mirror on the other side. So, we have to place this convex mirror. You can imagine the convex mirror to be somewhere over here. Okay? Yes, this is our convex mirror. And we have to place this convex mirror so that our final image is coincident with the original object itself. So, where must we have the final image? Our final image should be at the location of object itself. So, this was the location of the object, and this indeed is the location of the final image. Now, you can see, if our final image is over here, our final light rays should meet at this point, right? Right. Now, if these light rays are meeting at this point, this means the light rays have retraced their path. If the object and image are at same position, this means that in this case, our light rays must have retraced its path after getting reflected from this mirror. So you can imagine these light rays were going to touch the mirror, and after they touch the mirror, they get reflected back so that they retrace their path. And once they retrace their path, they will pass through the lens, and again they will undergo refraction, and again they will retrace their path, and finally they go and arrive at the same location from which they were emerging out of the object. Okay? Okay. So, this is what is happening. If the light ray have to retrace its path, it should fall perpendicular to the surface of the mirror. This means that this angle must be 90 degree. If the light rays fall perpendicular to the mirror, then they can retrace their path. Okay? Okay. So simple. So this means if our final image was somewhere over here, we can say this is V. This would have been V. But we have placed the mirror and our light rays are perpendicular to the mirror. Now, if the light rays are normal to the mirror, we know that if we extend these light rays, they will pass through the center of curvature, because all the normals to the mirror pass through the center of curvature of the mirror, right? Right. So, this center of curvature of the mirror is at a distance of 10 centimeter from the mirror. This was given in the question. Radius of curvature was 10 centimeter. Okay, okay. So we had to find the distance between the mirror and lens. What is this distance d? So this is very easy to find. How? We will first of all calculate the value of v, and then we will subtract 10 from it. Then we will get distance d. So d is nothing but v minus 10. This is how we are going to obtain d. Now, let me give you the key concept first. So the key concept to solve this question is this. For the image to coincide with the object, light ray must retrace its path after getting reflected from the convex mirror. Then only we can see our final image to coincide with the object itself. Okay? Okay. So this was the key concept to solve this question. Now let's return. We have to find V in order to solve this question. How to find V? Well, we can apply the famous formula, the lens formula. Do you remember the lens formula? Yes, we do. What is the formula? 1 by V minus 1 by U is equals to 1 by F. Awesome. Now, I will tell you a cool way to remember this formula. The most coolest way to remember this formula is like this. V is equals to UF divided by U minus F. U plus F. Okay? So, the formula is V is equals to UF divided by U plus F. Just remember this formula. This is so cool. Now, let's place the values and let's get the answer. So we take the direction of the incident light rays to be positive direction and the opposite direction will be negative direction. So we can see our object was on the negative side. That's why U will be minus 30. Okay, negative sign because the object is on negative side. Now focus is always positive for these converging lens. So F is equals to plus 20. Now let's place the values. So we are getting V is equals to minus 30 times plus 20 divided by minus 30 plus 20. Okay, so what is V? V is coming out to be minus 600 divided by minus 10. Minus cancels out, 1 0 cancels out, and we get V is equals to plus 60. So what is V? V is equals to 60. And we know the radius of curvature, this was given to be 10. So 60 minus 10 is the required distance. This is 50. This distance is 50. Okay. So let's see the options. We can see that option A, 50 centimeter is the distance between the lens and the mirror. So 50 centimeter option A is the right answer for our question. Rays from a lens are converging towards a point P as shown in the figure. Now see the figure. We can see some rays which are refracted from this awesome lens. They seem to converge at point P. They appear to converge at point P. But we place a glass slab and something entirely different is going to happen. So how much thick glass plate having refractive index 1.6 must be located between the lens and point P so that the image will be formed at P dash. So we have to tell the thickness of this glass slab so that instead of point P, the image is formed at a new point. The image is now formed at a point P dash. And you can see the distance between P and P dash is given to be 0.3 centimeter. So we want to shift the image by 0.3 centimeter. And what must be the thickness of our glass slab? This is the question. Got the question? Yes. Now, first of all, let's try to understand why there is a shift in the image. So I will try to explain that first. Suppose we have a ray, awesome ray going like this. Another ray is at some angle and we can see this ray goes like this. And they seem to meet at this point. We will call this point our image I. Now what if I place a glass slab or some slab of some material. So this is our slab of, let's say, thickness T. Good? Good. Now what will happen? Now we will see some refractions. So the ray of light will bend towards the normal at this point and then it will bend away from the normal. Cool. So we can see the image is formed at some other point. This is some other point. This is I dash. Got it? Got it. This is how the image is shifting. Let's say the shift is X. This is the shift. Now, can we find the shift? Well, yes. There was an interesting relationship between this shift and the thickness of our glass slab. Let's say the refractive index is mu. So we can say X is equals to T times 1 minus 1 by mu. This is how we calculate the shift. Okay? Okay. What if there are multiple glass slabs? Well, for each slab, we will write such a formula and then we will add up all the shift so that we can get the total shift. Okay? Cool. Now let's proceed. So in our question, we can see the refractive index was given to be 1.6. This was the refractive index of this glass plate. Now, let's find the shift. What was the formula? The formula was normal shift is equals to T times, in brackets we have 1 minus 1 by mu. Now, do we know the normal shift? Yes, we do know. It is 0.3 centimeter. So let me just write 0.3 centimeter over here. And then we have T times 1 minus 1 by mu. What is mu? Mu is 1.6. So we have 1.6 over here. Cool? Yes. Now this thing can be written as 0.3 is equals to T times. Now when we see this, we can just say that this is 1 minus, we have 10 divided by 16. 10 by 16 is nothing but 5 by 8. So this is 5 by 8. Okay. So we can see 0.3 is equals to T times 3 by 8. And now we get T is equals to 0.8. This is the thickness of our glass plate. Got it? Got it. Now let's see the options and we can find option A to be the right answer for our question. The plano-convex lens refractive index is given to be 3 by 2 of radius of curvature 10 centimeter is placed at a distance B from a concave lens of focal length 20 centimeter. So what is given? We have a plano-convex lens and its radius of curvature is given. Now by radius of curvature we mean radius of curvature of this curved surface. Radius of curvature of the other surface, which is a plane, is actually infinity. Yes? Yes. Now this lens is at a distance B from a concave lens. And we know what is the focal length of the concave lens. That is given in the question. That is given to be 20 centimeter. Alright. Now what should be the distance A of a point object O from the plano-convex lens such that the position of the final image is always at the same distance from the concave lens? So what do we have to find? We have to find what is this distance A. And what is the condition? The condition is our final image should always be at the same distance from concave lens. Let's talk about this now. Our final image, we want it always at the same distance from the concave lens. Now let's imagine a concave lens. So let's say this is the concave lens. Now our final image should always be at the same distance from this lens. So what should be our incident light on this lens so that the final image is always at the same distance? Even if we change the location of the lens, our final image should not change. Now what should be the incident light on this lens? If you can guess, our incident light must be like this, parallel to the principal axis. And we can see that when we have such kind of incident light, even if we change the location of this lens, then also the final image will always be at the same distance from this lens. Where is the final image? At the focus of this lens. So if we move the lens, the focus of this lens will always move with the lens. So the final image will always be at the same distance from this lens, at the focus. So we can imagine the rays after refraction, they will appear to meet at this point. At this point, we will get the virtual image. So this is the focus. Now, in order to satisfy this condition, this means the rays emerging from plano-convex lens must be parallel to each other. Okay? Okay. And then they go towards the concave lens. So our rays appearing from plano-convex lens must be parallel to each other. Now this means when the incident light goes towards the plano-convex lens, the incident light must go from the focus of this plano-convex lens, because then only they can appear parallel on the other side. Okay? Okay. So this means point O must be at the focus of this plano-convex lens. Okay? Okay. Now, this lens has obviously two focus. At one of the focus, we have to place the object. This is the focus, we will call it focus F1. Okay? Okay, nice. Now, let's find out what is the focal length of this plano-convex lens. If we can do that, we know what is the distance A. Distance A is nothing but that focal length. So this will come out to be F. Nice? Nice. Now let's try to see what is the focal length of plano-convex lens. For that, we will apply lens maker's formula. Let's make this lens. So we know the formula. This is our famous formula. Now let's see what are the terms. So 1 upon F. F is the focal length of this plano-convex lens. We have a mu of lens divided by mu of medium minus 1. Mu of lens, this was given in the question to be 1.5. And outside medium is air, so we don't have to worry about that. So mu medium will be 1. And then we have to subtract 1 from it. So 1.5 minus 1. And then what? Then we have 1 upon R1 minus 1 upon R2. So for the first surface, you can see the radius of curvature was given. It was given to be 10 centimeter. So we have 1 upon 10. And minus 1 upon R2. What is R2? For the second surface, what is the radius of curvature? It is infinity. Oh, infinity. 1 upon infinity is 0. Awesome. So what are we getting? We are getting F as 20. So 20 is the focal length of this plano-convex lens. So where should I place the object? 20 centimeter behind. So this A must be 20. Okay. Got the answer? Yes. So let's just find out the answer in the options, and we can see that option D, 20 centimeter, is the right answer for this question. The focal length of a convex lens in air is 10 centimeter. So sweet. Find its focal length in water. So we imagine a convex lens in air. We can see the focal length of this lens is given in the question, 10 centimeter. Now we place this same lens inside liquid. So our liquid is water in this case. Now the focal length will change. Yes. So we have to find the new focal length. Understood the question? We have to find the new focal length. Now let's see what is happening. Let's take the case of air. The focal length was given to be 10 centimeter. It was already given. But now we will apply lens maker's formula, and let's see what values can be obtained from that formula. So lens maker's formula, I hope you remember that formula. So when we apply this formula, when the object is in air, this is the formula. We can see 1 upon focal length in air. This is equal to refractive index of the glass with respect to air. This is nothing but 1.5, and we will subtract 1. And then we have 1 upon R1 minus 1 upon R2. So 1 upon R1 minus 1 upon R2. These are the radius of curvature of the first surface and the second surface. Okay, this is the first surface, this is the second surface. Now we know what is the focal length in air, so we can just put 1 upon 10 like this. And now you can see that we are getting 1 upon R1 minus 1 upon R2. This is coming out to be 1 by 5. So we will use that when we have to find the focal length when the lens is placed in water. So this is the relation we are going to use. Remember this. 1 upon R1 minus 1 upon R2. This is 1 by 5. Now, let's take the case of water. When we place the lens in water, we will apply this new formula. 1 upon focal length in water. And now we will have refractive index of the glass with respect to water. This is mu glass divided by mu water. So this was 1.5 and refractive index of water was 4 by 3. So let me take the 3 upstairs. So we are getting this. Let me subtract 1. Now we have 1 upon R1 minus 1 upon R2. What was that? You remember 1 upon R1 minus 1 upon R2 came out to be 1 by 5. Okay. So let me just write 1 by 5. Oh ho. So from this we can calculate the focal length in water. Exactly. And you can see the focal length in water is coming out to be about, let's see, we have 8 fives are 40. 40. Okay. So focal length in water is coming out to be 40 centimeter. And now we can just mark option B as the right answer. So what did we learn from this question? When the object was in air, the focal length was 10 centimeter. And when the object is in water, its focal length has increased. It became 40 centimeter. So the key takeaway for this question is, when lens is immersed in water, then the focal length of the lens increases as compared to that of the air. Okay? Remember this. So we can change the focal length by changing the outer medium. So awesome. So option B is the right answer for this question.